Alright, so we are going to do something called integration by parts. Integration by parts. This is aptly named because I'm going to give you basically an input-output machine, an equation, that you don't necessarily need to know how we got this equation. If you want to go look up the derivation, that's fine. You can go do that. But this equation will take complex things, integrate one part of it, and leave a leftover integral that hopefully we will be able to solve at the end of it. It just takes chunking as we're going through there. We use this integral, or this machine, for things like this. X e to the x dx. Leo, what operation is going on in between those two functions? Multiplication. So remember how in U sub I talked about the main uses of U sub were for composite functions, and anytime I have multiplication and division. Really, this is what I'm going to use for multiplication. This is the asterisk that I included. A lot of times we're going to use integration by parts for multiplication, but not necessarily just any old multiplication. Let me give you another example. Let me see if we can define that a little bit better. What if I gave you this? X squared ln of x dx. That's also something I'm going to use integration by parts for. So what do you notice about these two integrals? It's multiplication.
You can sub each one of the x to...
I could, yeah. What?
U for the x values.
Right. Here's what I'm trying to get you to notice. I have two different types of functions. One of them is an x. One of them is a weird function, an e to the x, a transcendental function. One of them is an x squared. Then I have a natural log. So it's multiplication of two different functions, or two different types of functions. That's really when I'm going to use integration by parts. If I have something that's multiplied, bless you, and one of them is like a weird ln of x, e to the x, cosine of x, something like that. What if you had something like this? Cosine of x divided by x cubed. That doesn't necessarily look like what we talked about, but could I rearrange it so that it was so? Yeah, how could I rearrange it?
X to the negative 2.
That's a cube down there.
Cube, my bad.
Right, I could rearrange this using our old trick that we for some reason hate. Negative exponents, cosine of x, dx. And then I could actually arrange this in a way that I could use this thing that I'm hinting at but haven't told you yet. Cool?
Cool.
Alright, here is the big input-output machine. This is the equation that you will use for integration by parts.
You have to memorize this one?
Yeah, it'll go on your yellow sheet. There's going to be weird parts in this to begin with. Don't panic. It's going to look strange. If I have the integral of something times its differential, that's going to be equal to, that's a u and that's a v. That's going to be equal to u times v minus the integral of v du. Bless you.
Thank you.
So this is my integration by parts equation.
And that's where you can...
Again, I'm just giving you the equation. I said the color red is red. Boom. Let's see what these parts are and where they go. So let's look at a fairly simple example to begin with. So look at the integral of x e to the x dx. Let's look at that first one I threw at you. Now, I'm going to choose the parts at the beginning, and then later on we're going to talk about why I'm choosing the parts in the way that I am. I need, from the integral, I need to pick something that represents a u component and something that represents a dv component. I'm going to need to separate this, the two parts, and get a u component and a dv component. And I see in my equation that I'm going to need to go from dv to a v, and I'm going to need to go from a u to a du. So I'm basically doing derivatives and integrals at the same time to chunk off a part. So I'm going to choose my u, in this case, as the x.
Is it because there's a dx?
No, not necessarily, because the e of the x and dx, they're still related. I'm going to choose my dv as e of the x dx. And again, for now, you don't really see the reasoning. I'll explain it in just a minute. I need to find a du component. So to get from u to a du, what operation would that be? Derivative. So the derivative of x, if I'm talking in terms of differentials, would be 1, but I'm going to write dx. The derivative of x is dx. To get a v component from a dv component, what operation would I be doing there? Integrating. So the integral of e to the x dx is going to be what? E to the x. So I chose two bits. I got their pairs. Hopefully I can just throw this all in my input-output machine and get an integral that is solvable. So this is saying it's going to be u times my v. So u was x, v was e to the x. So x times e to the x minus the integral of v. My v was e to the x. My du was dx. Now, can I integrate that leftover remaining part?
Yes.
Yeah, what is the integral of e to the x?
E to the x.
Great.
Do we have to do plus c?
Yep.
So would we have to have done it for the v equals 2?
Only 1 at the very end.
Okay. So x, wait, whoa.
So, let me...
Can't subtract that, right?
Right, you can't subtract it because that has an x. Let me explain what this machine is doing, right? I got these parts and I isolated this. It basically integrated a part of it and then said what is left over after I integrated that bit and piece of it. The bit that was left over was this integral. And luckily for us, that integral that was left over, I can actually look at, integrate it immediately, and I'm good and golden. Cool? I'm going to wait until the next one to show you why I picked what I picked. Let's do one more, and I'm going to show you the opposite and why it's not true, why you don't want to pick it the opposite way. So here's my next example. Let's look at the integral of 2x times sine of x dx. Alright, first off, Wesley. Well, let me let you finish copying it first. Sorry, Wesley. This 2 is a what? It's a constant. And again, if I can help myself, I don't want to have numbers floating around while I'm trying to integrate stuff. So what can I do with that constant, Wesley? Let's move it out front. Boof that bad boy out front. Sine of x dx. So, 2 way out front. I'm going to choose my u as my x, my dv as my sine of x dx. And again, take the dx with it, because if that dx isn't there, A, I haven't taken everything from the original problem, and B, I can't integrate something that doesn't have a dx. I need something that says, great, what am I integrating with respect to? Integrating with respect to x. Alright, shout out to my pairs. I need to find their pairs.
What kind of pairs?
The green pair? There are different types of pairs?
Yes, there's Moss pairs, there's red pairs, blue
Oh,
Marley pairs,
No.
there's Asian
Stop
pairs.
naming employees.
Oh, there's small pairs.
Alright, so my du, Derivative of x will be what? dx. My v, I need to integrate that. Integral of sine is what? Oh, negative cosine. Let me give you a very dumb, and that's not PC, but the integral of sine is a memory hook.
Why are they using these? Oh my gosh.
Oh my goodness. Integral of sine. The integral symbol somewhat looks like what letter? An S. SS. The SS police. You know who they were?
Yeah.
They were the secret police for the Nazis. They were pretty bad guys. They were pretty negative guys. So the integral of SS is going to be negative. So if that helps you remember that the integral of sine, that's the one that gets negative. There you go. Alright. I have integrated my parts. I've got my u's, I've got my v's. So let me plug them into my equation. But be careful. This 2 I pulled up front immediately. That 2 needs to be multiplied by everything that's going to come after it. Because I pulled it out at the beginning. I said this 2 is in there, but I'm going to pull it out at the beginning. So it's 2 u times v. So x times negative cosine of x minus the integral of v du. So negative cosine of x times dx. Norvik asked this a minute ago. I only need to add a plus c at the very end. Don't add multiple plus c's. Just at the end, this one integral is going to have one constant in there. Don't worry about it. Let me clean this up just a little bit. 2 negative x cosine of x. This negative is still a coefficient. It's a negative 1, so what can I do with it? Put it up front, so it's going to turn into a positive integral of cosine dx. Not all the way up into the front. You only put it in front of where the integral symbol is. You're not going to throw it all the way up here, because this part has already been integrated. You're not going to do that.
Negative in front of the cosine.
The negative and negative turned into a positive. This negative went right there.
The integral sign is act as a coefficient, like the 2 words.
It sort of does, yes.
So you wouldn't multiply it up times everything up front?
No. So the integral of cosine is what? A regular sign. So this is 2 parentheses negative x cosine x plus sine of x plus c at the end. I'm excluding that plus c on the outside because it's a constant. I'm not going to say it's 2c. Constant is just like a black hole. I have no idea what it is. It could be a 5, whatever. At this point, I'm not going to manipulate that constant by this coefficient that's up front. I'm just going to include it at the end by saying, great, there's something out there that it could be. It's not going to be 2 times it. It's just going to be whatever that is. Now, here comes why I chose what I chose. If I had rearranged them and I had chosen my u as my sine of x and my dv as my x dx, if I went this route, I can take the derivative of this. The derivative of sine is what? Derivative of sine is what? Cosine. Then the integral of x, to find my v, what is the integral of x? X squared over 2. Now, if I were to do that, it would be u times v, that one's fine, x squared over 2 times sine of x, that's cool, minus the integral of these two things. I started off with x sine of x. I am now trying to integrate x squared cosine of x. Have I made my problem easier or harder? Harder. I've made it harder. The exponent's going up. And if I continue this process and I try to do it again, it would go up to a cubed. It would go up to a fourth. It would keep going up and up. So I've made my problem a ton harder by choosing the wrong terms.
So how do you know which one's right?
For now, You sort of just have to guess. You have to look at it. And luckily for you, there's only 2 guesses that you can do. You can choose this as your u, this as your dv, or flip them around. Or you can look at this by saying, great, if I take the derivative of this portion, it's going to go away. And I've made my problem easier. Okay. Alright. I want you to try one on your own. The derivative of x, Allison? What's the derivative of x? Dx. So it goes away. I get rid of the x component. I just have that differential, which I can therefore integrate. Cool? Like the derivative of x is just 1. It disappears. It goes away. Here's one I want you to try on your own. Integral x squared ln of x dx. Now, when you choose, this one is going to sort of go opposite of the idea I just told you, and I'm doing this on purpose because I want you to think about it. When you choose your u and your dv, make sure that you can truly take the derivative of whatever you choose your u as, and you can truly integrate whatever your dv as. Because if you can't integrate one of those parts, don't choose it as your dv. You can't do anything with it. So, that's my hint to you as you try this. Figure it out. Try it on your own. Alright, in this case, I'm going to choose my u as natural log of x. My dv is equal to x squared dx. The reason being, do I know the integral of natural log? No, so this big old rock sitting on that pathway saying you can't go down this way. You haven't unlocked this map yet. Thank you, Jacob. Very cool. So du is going to be equal to 1 over x dx. And v is going to be equal to, I'm integrating this, the power is going to go up, so x cubed over 3. If you are totally lost and you forget your equation and what order they go in, as long as you set this up u dv and you find their pairs, the equation will always be these two on the diagonal minus the integral of these two on the side. To give you a visual representation of what the equation is, it's always uv minus the integral of v du. So it's always diagonal and up and down if you're setting it up in the same way every single time. Cool? So this will become natural log times this. So x cubed over 3 times ln of x minus the integral of this business. So integral of x cubed over 3 times 1 over x dx. And this is why this worked out nicely, because I got rid of one of the equations so that both of the equations I want to integrate at the end are the same. They are similar. X cubed over x, that simplifies into a what?
X squared.
X squared. The over 3 can go where? Out front. So this is x cubed ln of x over 3 minus 1/3 integral x squared dx. The 1/3 is just a number. It's not a function. It is a coefficient. So I can take it out front because I don't want to look at that as a division problem. I want to eliminate any constants I can. Integral of x squared. I can do that. What is the integral of x squared? X cubed over 3. So all told, this is x cubed ln of x over 3 minus x cubed over 9 plus c, because of the 1/3 that I will get as I integrate it, times the 1/3 that was already there. Everyone's somewhat seeing the pattern as it's going through there, yes? Alright, let's do one more together for something that you will likely see on a test or the AP test.
Wait. Let's go back. I didn't see Okay, cross out.
I want to do this one with you. There's something that's going to happen that's different in this one. You can try. You're just going to have to beat me to it. Alright. Here's our example we're doing. Melanie, I'm going to give you an example of trying your own after this. Here we go. Integral x squared e to the 2x dx. Now, again, let's try and think before we choose our e to the x or your u's and our dv's. Can I take the derivative of both of these? Absolutely. Can I take the integral of both of these? Absolutely I can. So, I have to be more efficient. Which one, when I take the derivative of it, will likely disappear? An x squared or an e to the 2x?
X squared.
X squared. If I take the derivative of an e to the x, I'm going to get an e to the x. And the e to the x will keep popping up, keep popping up, keep popping up. So I'm going to choose my u as x squared and my dv as e to the 2x dx. Again, that's the train of thought I'm going through as I pick my u's and my dv's. I like turtles. So my du is going to be equal to 2x times dx. Now, this is an integral that we can maybe get to the point where we can do it in our heads, but if you try and do this in your head and you fail, the result is miserable. So let me go up here and do this integral. It is not e to the 2x plus c. E to the 2x dx. I'm doing that. It is neither that as well. Yeah. There you go. So, the u is equal to 2x. I know the integral, Jacob. The integral on my card is e to the variable, not e to the 2 times that variable. I don't know that. I know just e to a singular lone variable. So to get rid of 2 times that variable, I'm going to do a very simple u sub. So du is equal to 2 dx. So du over 2 is equal to dx. So this integral is e to the u times du over 2. Now, that over 2 is a what? Coefficient. Boof it up front. So it's 1/2. What's the integral of e to the u? E to the u. So all told, this integral is 1/2 e to the 2x. Now, again, that's what I'm saying. Hopefully, we get to the point where we can look at that and say, great, it's just a coefficient times a singular variable. It's going to be my integral that I know in my head divided by that number. So it's e to the 2x divided by 2. But until we get to that point, make sure you're doing the very simple u sub to get there.
So we're dividing by the coefficient in front of the variable.
Correct. Alright. Now, I go through my machine. It's u, v. So, x squared times 1/2 e to the 2x minus the integral of v du, so 1/2 e to the 2x times 2x dx. I need to clean this up a lot before I can see what's going on through here. This is x squared e to the 2x divided by 2. The 1/2 and the 2 do what with each other? They cancel. So the integral of x e to the 2x dx. Now, I'll give you a second to catch up. Claire.
Wait, where'd the x come from?
Wait, so that's going to be x,
The 2 and the
that's going to be x
1/2
squared
cancel each other
times
out.
e to the 2x over 2, right?
Yeah, sort of.
Huh?
Oh.
X right there.
There you go.
Alright, now, Can I look at this integral? Up until this point, I integrated a part out, and I got an integral that I can solve just by looking at it. Can I do that for this integral? No, but I have something times something. What process do I do for integrals where it's something times something? Not USUB, integration by parts. I just have to do it one more time. Because I haven't gotten rid of... Yes, it's like low talks. Yeah, so I got to do it one more time. I know, this is the worst thing that has ever happened to you.
I cried.
Dude, if you're crying now.
What do you mean by that?
What's gonna happen later?
What other demons do you have in store for us?
So, the U...
Wait, we're not doing the front part of that, right?
We're not doing the front part. The front part is the part that I already integrated out. It's done. I'm just looking at this integral now. Right here. So du, Jacob. Now, luckily for us, we've already done this integral before. Integral of e to the 2x is 1/2 e to the 2x. Please be very careful. This negative right here is going to the entire integral. And I'm going to split this integral into two parts. So what do I need to do with that negative? I need to distribute it. So this is x squared e to the 2x over 2 minus everything that's about to come after it. So u times v, so x e to the 2x divided by 2 minus, I have a new integral, which is these two, v du. So the integral of 1/2 e to the 2x times dx. Now I've finally gotten rid of that pesky x. It took me a couple steps, but I got rid of it, and now I just have the integral of an e to the 2x. Integral of e to the 2x is what? E to the 2x divided by 2 with another 1/2 there. So the divide by 2 and the 1/2 are going to turn that into a what? 1/4. Distribute this negative.
Hey, what'd you say, Luke?
He's integrating that final part.
Yeah, that sounds simple.
What?
Plus.
Yes, doesn't that cancel out?
That one has an x, that one has an x squared. Different terms.
Oh my god, I did not see that.
Now, for those of you that are confused why there's a 4th right there. The 1/2. Stop talking. Shh.
No, why? You gotta like write out all the steps.
No, I don't.
I understand.
You got to listen to me.
You confused me.
Then listen to what I'm saying instead of trying to talk over me. There's a 1/2 right here, yes?
Yes.
That's a coefficient. It can go up front. What is the integral of e to the 2x?
E to the 2x.
Half e to the 2x.
Half e to the 2x. So I have another half. When I integrate this, the half that was here, then the half that is right there, 1/2 times 1/2 gets me what? A 4th. And so it's over 4. The negative right here distributed here, so it's negative. The negative makes it a positive. So this integral, if I had rewritten it, was 1/2 integral e to the 2x dx. So it's 1/2 times 1/2 e to the 2x. That half and half make a 4th. Alright. That's really only a curveball I can throw at you. I can throw one other curveball at you, but you're not going to see it. So I'm not going to throw it at you.
Yeah, I usually don't say her.
So you're going to hit me on the test, or is it like...
No. Here's the last one I want you to try on your own.
Just take this right over to the next.
If I knew that meant, it's probably really helpful.
Here you go. Here's the last one. Try it. Integral x squared cosine of 3x.
But this is problem 2.
Try that one on your own. You are ready. I've put the answer up here so you can check it once you've gotten down to the end. but only do it once you've gotten it down.